Hi everyone, welcome to Pathways to Chemistry. This is Dr. O'Connor. Today we're going to look over Chapter 10 and we're going to talk about electron configurations. Here we have the periodic table and we'll go back to that in a few minutes. So let's first talk about how the electrons are distributed about the nucleus of the atom. It turns out that each electron is restricted to moving within certain regions of space within the atom, so they're not just randomly distributed about the nucleus. So this is determined by the amount of energy the electron has and the number of electrons that have different amounts of energy, which in turn is determined by how many electrons are present in a given atom. We say that the energies of electrons are quantized. That means that they're restricted to having certain values. So, for example, when, let's say you're turning up the volume on a radio. So, when you turn up the volume on a radio, we start from zero, turn up the volume. It turns out that even if you turn up the volume very quickly, we're going to hear all of these volumes are included from low to high. When we talk about something being quantized, just imagine now if you were to turn the volume up and first you would get this volume, then this, and then this volume, and then this higher volume, but nothing in between, okay? So in other words, those volumes would be restricted to certain volumes or values. Well, that's how it is with an electron. So here, if this were energy, okay, so we have this little plot here, energy, we have an electron. The electron can have this energy, or this energy, or this energy, but it can have nothing in between these steps, if you will. So that's what it means to be quantized. So electrons are grouped around the nucleus into energy levels, which we call shells. And an energy level is a grouping of electrons in an atom according to energy. So we call these shells the principal energy levels. And we represent the shell with a lowercase n, and we can have n equal to 1, n equal to 2, n equal to 3, and so on. So this would be the first principal energy level, or the first shell. This would be shell number 2, or the second principal energy level, shell number 3, or the third principal energy level. It turns out that within shells, electrons are further grouped into subshells, also called sublevels. And just like the shells, for example, shell number 2 is higher in energy than shell 1, shell number 3 is higher in energy than 2, shell number 4 is higher in energy than shell number 3. So as n increases, so does the energy. So the subshells are also identified in order of increasing energy, and we assign the letters S, P, D, and F to these subshells. So S would have the lowest energy, and then P, then D, and then F. Okay, so F would be higher in energy than S. D would be higher in energy than S. Now, we'll find as we start writing electron configurations, there's some exceptions here, and I will point those out. So, we have the shell number, or n, equal to 1. There is one subshell, and that's an S subshell. For n equal to 2, we have 2 subshells, and that would be an S and a P subshell. Notice that the shell number tells us how many subshells are within that shell. N equal to 3, we have an S, a P, and a D subshell. And for n equal to 4, we have an S, a P, a D, and an F subshell. So again, the number of subshells is equal to the shell number, or the principal energy level, N. Within each subshell now, we have electrons that are grouped into what we call orbitals. And an orbital is a region of space around the nucleus where there's a high probability of finding a given electron. So this is all based on quantum mechanics. We're not going to get into the quantum mechanics here in this course. We want you to have a basic idea of how the electrons are grouped about the nucleus. So it turns out in an orbital, we have a maximum of 2 electrons. So a maximum of 2 electrons can occupy an orbital. 3 electrons cannot occupy an orbital. 4 electrons cannot occupy an orbital. 1 electron can occupy an orbital, and 2 electrons can occupy an orbital. So the maximum number of electrons that can occupy an orbital would be 2 electrons. Oops, let me go back here. So let's go ahead and summarize this. I put this table together to show you. So here is our shell number, or N, okay, equal to 1, 2, 3, and 4. So in shell number 1, we have 1 S subshell. In shell number 2, we have 2 subshells, an S and a P. Shell number 3, an S, P, and D subshell. Shell number 4, an S, P, D, F subshell. Now, it turns out that an S subshell has 1 orbital. That means that the maximum number of electrons in the S subshell would be 2. So that means for n equals 1, the maximum number of electrons would be 2. Now, let's go to n equal to 2. And we know that there are 2 subshells, an S and a P. We know that an S subshell has 1 orbital, and it contains 2 electrons. A P subshell, it turns out, consists of 3 orbitals, 3 p orbitals. And remember, we said that each orbital can hold a maximum of 2 electrons. So the p subshell can hold a maximum of 6 electrons. That means that for n equal to 2, the second shell can hold a maximum of 8 electrons. So now we go to shell number 3. That's composed of a S, P, and D subshell. And again, the S subshell is 1 orbital, 3 orbitals in a P subshell, and it turns out there are 5 orbitals in the D subshell. That means that the maximum number of electrons is 2 for the S orbital. We have 6 electrons for the 3 p orbitals, and 5 times 2, 10 electrons for the 5 d orbitals. That's a maximum of 18 electrons in third shell. Now, for n equal to 4 subshells, S, P, D, and F. And again, the S subshell, 1 orbital, 2 electrons. We have the P subshell, 3 p orbitals, a maximum of 6 electrons. The D subshell, we have 5 d orbitals for a maximum of 10 electrons. And the F subshell has 7 orbitals for a maximum of 14 electrons. So shell number 4 can hold a maximum of 32 electrons. So here's a question for you. How many electrons are present in an atom that has its first and second shell filled and has 3 electrons in its third shell? Let's see. If its first shell is filled, that means there are 2 electrons. And if its second shell is filled, that's 8 electrons. And then it tells us it has 3 electrons in its third shell. So that's a total of 13 electrons. Now it tells us to name the element. Well, we're looking at neutral atoms here. So what we can do is go back to the periodic table, and 13 electrons means 13 protons, and again, that's for the neutral atom. So the element here would be aluminum. We're talking about orbitals, and again, I can't stress this enough. Each orbital can hold a maximum of 2 electrons, and the electrons must be of opposite spin. Again, this is just a summary here. An S subshell consists of 1 orbital, P subshell 3 orbitals, D subshell 5 orbitals, F subshell 7 orbitals. So let's just take a look at these orbitals. These are regions of space where the probability of finding a given electron is high. So an S orbital is spherical in shape, like this. So what that means is you're most likely going to find the electron closer to the nucleus, but you can find that electron anywhere in this region. For the p orbitals, we have 3 p orbitals, and notice here that the p orbitals consist of these 2 lobes, and so the electron, the highest probability of finding an electron is within these regions of these lobes. So the 3p orbitals are oriented at right angles to one another. Now let's go ahead and look at let's go ahead and look at the 5d orbitals. These are even more complex in shape than the p orbitals. So these d orbitals are, again, they're high energy. They're very complex as far as the shapes go. And so we have 1, 2, 3, 4, 5 of these orbitals. And again, the electron is most likely to be found within these shaded regions. Okay, and this kind of gives you an idea of we have an XYZ axis of the 5d orbitals, the orientation of the 5d orbitals. Now, some questions. What is the maximum number of electrons that can occupy a 3p subshell? We know that a 3p subshell or sublevel, we have 3 orbitals in a 3p subshell. So the maximum number of electrons that can occupy a 3p subshell would be 6. A 2s subshell. By the way, this number here is the shell number, okay? So an S subshell, I don't care if it's a 3s, a 2s, a 4s, an S subshell can hold 2 electrons. Same here, we talked about a 3p subshell. It could be a 2p subshell, a 4p, a 5p subshell. It can hold a maximum of 6 electrons. A 5p orbital, well, we said an orbital can hold a maximum of 2 electrons. So I don't care if it's a 5p orbital, a 5d orbital, a 4f orbital. An orbital can hold a maximum of 2 electrons. Shell number 3 can hold a maximum of 18 electrons. Remember, we've got an S, P, and I'm really sorry about this. We have S, P, and D subshells. So a maximum of 2 in the S, a maximum of 6 in the P, and a maximum of 10 in the D. So that's 18 electrons. And then a 3D subshell, well, a D subshell, whether it's a 3D, a 4D, or a 5D, can hold a maximum of 10 electrons. So now, electron configuration. It's a specific arrangement of electrons in the atoms, shells, and sublevels. So there are 3 rules. Electrons will occupy the lowest energy orbitals available, starting with 1s. Each orbital can hold only 2 electrons, and they must be of opposite spin. Orbitals are each half filled by 1 electron before you can start pairing the electrons in the orbital. So before we start writing electron configurations, let's look at this diagram here. This is energy going from bottom to top, so energy is increasing. So the 1s fills first, 2s, then the 2p, the 3s, and then the 3p fills. Here we have the 4s. Now here there's a bit of an energy crossover. After the 4s, the 3d orbitals fill, then the 4p orbitals. We then have the 5s orbitals fill, the 4d fill next, and the 5p fill next. Down here, I have the filling order here. So after the 5p, the 6s fills, then the 4f, the 5d, the 6p. Then the 7s, the 5f, the 6d, and the 7p. So let's take a look here at how this works. There are 2 ways that we can represent an electron configuration. And the first way is the SPDF notation. And what we do is we use a number to designate the principal shell. And we use a letter S, P, D, or F to identify the subshell. And then we have a superscript which will indicate the number of electrons in a particular subshell. The other way to represent an electron configuration is with an orbital box diagram. So we have boxes, or sometimes what I'll do is I'll just draw these horizontal lines. So this would be a 1s, this would be a 2s, and then this would be a 2p subshell. So here we show nitrogen. The 1s fills first. We have the 2 electrons, both of opposite spin. The arrowheads are opposite one another. So that one fills first. The 2s fills next. And if we go back to the periodic table, before I continue with this, we go back to the periodic table, we see that nitrogen has 7 electrons that need to be distributed. Right? So again, these are neutral atoms that we're writing the configurations for. So 2 of the 7 are in the 1s, the 2s fills first, and then the remaining 3 electrons go into the 2p. I will tell you right now, notice that we don't pair electrons until each orbital in a subshell is half filled. So let's do a few examples. Let's see, I think that we can write the electron configurations for, I'm just looking for my periodic table here. Let's go ahead and write the electron configuration for fluorine. And then we'll write an electron configuration for magnesium. And then we can write one for, let's see, we'll write one for iron, which is a transition element, and then we'll write one for iodine. So we're going to write both the SPDF notation and we'll do an orbital box diagram. Now, fluorine has atomic number 9, so that means 9 protons, and it's a neutral atom, so there are 9 electrons to distribute, okay? So we have a 1s, so 2 electrons will go in the 1s, okay? And then we have 2 electrons in the 2s. And then we have the, and again, we have to know the filling order, and then the remaining electrons will go in the 2p. So 5, 6, 7, 8, 9. 2, 4, 6, 8, 9 electrons. So this is the orbital box diagram. Here's how I write the SPDF notation. I have 2 electrons in a 1s, so that'd be 1s2. 2 electrons in the 2s, so that'll be 2s2, and I have 2, 4, 5 electrons in the 2p subshell, and I would write it like that. So both the orbital box diagram and the SPDF notation. The next one is magnesium. Magnesium, we're looking at atomic number 12, so that means 12 protons, 12 electrons. So again, I'm going to go ahead and draw my... So in this case here, I've got 1s, 2s, the 2p subshell, and the 3s subshell. 2 electrons go here, 2 electrons go here, and then 5, 6, 7, 8, 9, 10, 11, and 12. So I can write this as 1s2, 2s2, 2p6, 3s2. Again, I'm following the proper order of filling. So now let's go to iron. Iron has 26 electrons. Okay. So the 1s, 2s, 2p, do a 3s, and then there'll be the 3p orbitals, and I think we'll have to go to 4s, and let's just start filling these. So this is the 1s, 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p. We have 2 electrons in the 3s, 6 electrons in the 3p. And then here we have 4s, so I have 2 electrons in the 4s. Now remember, this is where the energy crossover happens. Before the 4p fills, we have the 5 3d orbitals. So let's see, what do we have so far? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25. Remember, I can't start pairing until the orbitals are half filled. 26. So now from the orbital diagram, I can write my electron configuration. 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, 3s2, 3p6, 4s2, 3d, 2, 3, 4, 5, 6, 3d6. So that's the electron configuration for iron. Now we'll do the electron configuration for iodine. And iodine has 53 electrons. Okay, so we're going to have 2 in the 1s. We'll have 2 electrons in the 2s. And then we have 6 electrons in our 2p. And then we have 2 electrons in the 3s. And 6 electrons in the 3p. I should have made this bigger. We have 2 electrons in the 4s. Now remember, we're going to fill the 3d next. So we have the 5 3d orbitals. And that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in the 3d. And then we have the 4p, so 3 4p orbitals, 6 electrons in the 4p subshell. And then after the 4p, we have the 5s. So 2 electrons in the 5s. And then we have 10 electrons, 4d orbitals. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And let's see, we have 5 electrons left over. They're going to go into the 5p orbitals. So we have 1, 2, 3, 4, 5 electrons. This is the 5p subshell. So we would have, if we count these up, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 53 electrons. Now I can write the electron configuration. I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. So we have both the orbital box diagram and the electron configuration for iodine. So what you need to do is start writing these electron configurations, write the orbital box diagrams. You're going to need some practice before the exam. Now, what you can do is you can actually use the periodic table in order to write an electron configuration. It is arranged in such a way that if you read from left to right, you can write an electron configuration. So here's how we label the periodic table. Groups 1A and 2A, including helium, which is right here, are called the S block. Groups 3A to 8A, excluding helium, are called the P block. The transition elements are the D block, and the inner transition elements, the F block. Let me show you an example of how we could do this. Let's say we want to write the electron configuration for oxygen. So oxygen would be right here in group 6A. So I'm going to read from left to right. I start here, got 1s1, 1s2. So that's 1s2. Here we have 2s1, 2s2. So we have 2s2. And then we have 2p, 1, 2, 3, 4. So that would be the electron configuration for oxygen. Let's try writing the electron configuration for nickel. And nickel would be right here. And nickel has 28 electrons. Okay? So watch this. So again, 1s1, 1s2. So I write that. Here we go. 2s1, 2s2. I have 2p1, 2, 3, 4, 5, 6. So 2p6. 3s1, 3s2. And then we go over to 3p1, 3p2, 3, 4, 5, 6. So 3p6. Then we're here at 4s1, 4s2. And then we have 3d1, 2, 3, 4, 5, 6, 7, 8. 3d8. So that is the electron configuration for nickel, and that's just using the periodic table. And this is just another example of the blocks on the periodic table. So you can use either diagram, but you should take your periodic table that you use and label the S, P, D, and F blocks. The last thing we want to talk about is the valence shell. The valence shell is the outermost electron shell of an atom. A valence electron, obviously, is an electron in the outermost shell of the atom, or in the valence shell. So let's go back to where we did iodine. And the outermost shell that's filled is shell number 5. And iodine has 2 plus 5, 7 valence electrons. We'll go back here to oxygen. The outermost shell with electrons is shell number 2, and there's a total of 2 plus 4, 6 valence electrons for oxygen. Okay. So back to the periodic table. Oxygen is in group 6A. We just said that oxygen has 6 valence electrons. In fact, all of these elements in group 6A have 6 valence electrons. It turns out that for main group elements, the number of valence electrons is equal to the group number. So that's for 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. So for example, neon is in group 8A. It has 8 valence electrons. Sulfur is in group 6A. It has 6 valence electrons. Lithium, sodium, potassium, group 1A, 1 valence electron, and beryllium, magnesium, calcium, and so on in group 2A all have 2 valence electrons. So this is summarized right here. Group 1A, they all have 1 valence electron. Notice the N is the shell number. So that means, we'll go back to the periodic table here, that for period 2, or shell number 2, in group 1A, lithium has 1 valence electron. Shell number 3, group 1A, sodium, 1 valence electron, and so on. It turns out that because the electron configurations, or the valence shell configurations for elements in a group are the same, those elements have the same chemical properties. They behave similarly. So this means that, for example, all of the elements in group 1A, they have similar valence shell configurations. Therefore, they tend to behave similarly. The same for all the elements in group 2A. Again, their valence shell configurations are the same. So they tend to behave similarly. For main group elements, the group number corresponds to the number of valence electrons. I hope this helps. Make sure that you can write these electron configurations and the orbital diagrams for the exam.